All right, let's look at L'Hopital's rule. And L'Hopital's rule allows us to look at limits that are indeterminate forms. Okay, so indeterminate. I always used to spell this wrong. Indeterminate forms. And what that means is forms that we don't know what they are. And again, you might not have all these established, but there are 7 of them. So the indeterminate forms, or what happens if you look at a limit and you get 0 over 0. You don't really know what that is. 0 over 0 doesn't make any sense. Again, I'm looking at limits. I'm not actually looking at 0 over 0. I'm looking at what happens when I look at the limit of something and I get 0 over 0. I'm looking at infinity over infinity. Well, it's going to depend on which infinity is bigger. Maybe they're the same version of infinity and I get some finite number. Maybe the top is bigger. Maybe the bottom is bigger. L'Hopital's rule allows us to figure out with this. What about infinity minus infinity? Right? Again, which version of infinity is bigger? What about 0 times infinity? Again, I got to repeat myself. I'm not talking about 0 times infinity. An infinite number of zeros clearly is just 0. I'm looking at something really, really close to 0. But if it's really close to 0, but you have an infinite number of them, is it possible that that is some finite number? Well, maybe it is. Maybe it's 0. This kind of depends. We're going to have to look at different versions. That's why there's not a rule for it. That's why L'Hopital is a way that we can decide what these forms actually are. Remember, these are indeterminate forms. What about 0 to the 0 power? Same thing. I'm not talking about 0. I'm talking about something getting really, really close to 0. 1 to the infinite power. Again, not talking about 1. 1 times 1 times 1 times 1 times 1 is just 1 and always will be 1. But what if it's like 1.00001? But you're raising it to the infinite power. Is it possible that that is not then just 1? Well, L'Hopital's is going to decide that for us. And then also we have this same thing, infinity to like the 0. Right? And again, I'm not talking about 0. I'm talking about something really, really close to 0. All of these are limit things. Okay? You got to get out of your brain. Later on, we will have situations where we have 1 to the infinity. I'm like, oh, it's just 1. Of course it's just 1, but this is the limit. All of these are really just limits. Okay? So let's look at examples and then what the rule is. So what L'Hopital says is this. The rule says if I'm looking at f of x over g of x, and x can go to anything, right? X can go to a. Sometimes x, we're looking at the limit as x goes to 1. Sometimes we're letting x go to 0. Sometimes we're looking at x go to infinity. That's not the point. But if we look at this and we get 0 over 0 or infinity over infinity, L'Hopital says that this limit is equal to the limit of x goes to a of f prime of g over g prime. Again, we're not doing quotient rule. We just got to take the derivative of the top and the derivative of the bottom and then reapply the limit. And it guarantees that these two limits are equal. And again, we can only do this, only if we show that the original limit is one of these two indeterminate forms. See how these aren't fractions? So all of these are going to need manipulated. All of these guys, all of those cases are going to need manipulated until they look like one of those cases, and I'll kind of show you what I mean by that, right? These are our two main cases, and once we get either one of those, 0 over 0 or infinity, then we know what we can do. We can apply L'Hopital's and take a derivative of the top and a derivative of the bottom, and then reapply the limit, and then hopefully get some finite number, or infinity, or 0, and we know that then these two things are equal. Okay, so this is L'Hopital's rule, and these are the indeterminate forms. These are the forms in which we don't know what to do. So we do L'Hopital's. We don't know the answer. Okay, so let's go over some examples. So here's an example of 0 over 0. And this is a classic one because we've already done this. Let's look at the limit as x goes to 0 of sine x over x. Again, if you just plug this in, sine of 0 is 0 and x is 0, and we get 0 over 0. So we can apply L'Hopital's. So if you apply L'Hopital's, we can then look at the limit as x goes to 0 of the derivative of the top, which is cosine, and the derivative of the bottom, which is 1, and look at this limit. The limit of this, cosine of 0 is 1, 1 over 1 is 1, and we go cool, which means this particular version of 0 over 0 is actually equal to 1. Now that doesn't mean 0 over 0 is always equal to 1, then we wouldn't need L'Hopital's. Then this wouldn't be an indeterminate form. It's just that this particular version. Okay, let's do a different one, and I can show you that this 0 over 0 is not 1. Okay, example 2. Let's look at the limit as x approaches 1 of x cubed minus 1 over x minus 1. Again, if you just try to plug in the limit, you get 1 minus 1 is 0, 1 minus 1 is 0, and you get 0 over 0. This says, it's an indeterminate form. Let's do L'Hopital's. It's one of our two basics, so we can just go right to this. So then we can say that this is equal to the limit as x goes to 1 of the derivative of the top, which is 3x squared, over the derivative of the bottom, which is 1, and now we can plug in the limit and get 3. And we can show then that this particular 0 over 0 actually is equal to 3. And again, we can have an infinite number of results. 0 over 0 is going to be dependent on what really the functions are that make up 0 over 0. So this is kind of our basic cases for L'Hopital's. Again, our indeterminate forms. Once you get it, then you can kind of go to work there. Okay, so that's that first one. Let's do an infinity minus infinity case. Okay, so let's look at, how about if we looked at the limit of x squared over, 1 plus 3x squared as x goes to infinity. Well, if you plug in infinity, you get infinity squared, which is infinity. 1 plus 3 times infinity squared is infinity, and you get infinity over infinity. You're like, all right, don't know what to do, but L'Hopital justifies. So what L'Hopital will say is take the derivative of the top and take the derivative of the bottom. The derivative of the top is 2x. The derivative of the bottom is 6x. Well, 2x over 6x, that is just equal to 1/3. That's actually true for all x because the x's cancel. And we get 1/3, which is what you probably learned in Algebra 2. If you just compared the big dog to the big dog, you looked at that ratio. And again, why you could do that? Well, because L'Hopital justifies. So this particular infinity over infinity is actually 1/3. Let's look at a different case. What if I looked at the limit as x goes to infinity of x squared over e to the x? Infinity squared is infinity, e to the infinity is infinity, and you get infinity over infinity. So you can do L'Hopital. Take that, and L'Hopital says that those two limits are the same. The derivative of the top is 2x, the derivative of the bottom is e to the x, and you're like, oh, I get infinity over infinity again. You're like, oh man. But you can do L'Hopital's again, right? If this is the same thing, you can do repeated L'Hopital's. And so you can say that the red limit equals this new blue limit. So I can take another derivative. The derivative of the top is 2, and the derivative of the bottom is e to the x, and I get 2 over infinity. Well, 2 over infinity is not indeterminate. 2 over infinity is, in fact, 0, which is to say that this limit is 0, which is to say that this limit is 0, and we kind of know that. This is quadratic growth, and this is exponential growth, right? This is infinity squared over e to infinity. This is much, 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 much bigger. This infinity dominates this infinity. And so it's not surprising that we do, in fact, get 0. Again, infinity over infinity in this case is equal to 1/3. Infinity over infinity in this case is equal to 0 because it depends on the size of infinity, just like earlier. 0 over 0 was 1, 0 over 0 was 3. It depends. And that's the purpose of L'Hopital. It allows us to justify things like that. Again, we can go over as many examples as you want. All of them end up being the same thing. Let's look at the limit of 1 plus 1 over x to the x as x goes to infinity. This is an interesting case because what happens when you plug in infinity? You get 1 plus 1 over x, which is really, really close to 1. And so this is pretty much 1 to the infinity. But again, it's not exactly 1. It's something just bigger than 1. You're like, oh man, this is an indeterminate form, except I can't apply L'Hopital's. I need to make it a fraction first. You remember L'Hopital's, it has to be f of x over g of x before I do anything. And so in this particular case, I need to apply a logarithm. I'm going to apply the logarithm, and it turns out I'm going to find the limit of the logarithm, and then I'll get rid of the logarithm at the end. If I put a logarithm in this limit, that allows me to bring that x down in front, and I get x natural log of 1 plus 1 over x. Then this x I actually can put in the denominator. And so this is kind of a little trick that you're going to learn. So then I have 1 plus 1 over x. And instead of multiplying by x, I can put it in the denominator as 1 over x. And so now I can look at this limit as x goes to infinity. And what I've done is, if you plug in infinity here, you get 0 over 0. Check that out. So what I did is, I did some algebra, and I changed 1 over infinity to now 0 over 0. But once it's 0 over 0, now it is the indeterminate form that can go straight to L'Hopital's. Now I can take the derivative of the top and the derivative of the bottom. The derivative of a logarithm is 1 over u plus the derivative of that. The derivative of that is negative 1 over x squared, all over the derivative of that, which is negative 1 over x squared. That's just power rule. These conveniently cancel. And when I plug in infinity, I get 1 over 1 plus 1 over infinity. 1 over infinity is 0. 1 over 1 is just 1. So I get 1. But that's not the answer. Again, why is that not the answer? Because I found the limit of the logarithm. I put in this logarithm. So now I have to get rid of the logarithm by exponentiating. And so what I found was the natural log of the limit. The natural log of the limit is equal to 1. Again, the natural log of the limit was 1. So I exponentiate both sides. And then the limit, L, is actually e to the first, which is e. Again, if the natural log of the limit is 1, then the true limit is actually e. And so this particular version of 1 to infinity is e, and hopefully you recognize this from compound interest, right? 1 plus r over n, the nt is equal to the PERT formula, kind of that idea. Again, the limit here is e. And again, it's not always true. It's not like 1 to the infinity is always e. It's just that this particular version of 1 over infinity was e. I needed to do some algebra first to arrange it into a fraction. Again, look back at L'Hopital's. L'Hopital's says the limit of f over g, you got to get it into a fraction. So this didn't start out as a fraction. None of these indeterminate forms. Right, look back. None of these forms are fractions. So all of them need to turn into this form, which means turn it into a fraction. And the turning it into a fraction is just algebra. That's algebra stuff. Factoring, combining fractions, logarithms, exponentials, whatever, yada, yada, yada. All of algebra stuff turns these guys into a fraction. And then once it's a fraction, then you actually can apply L'Hopital's. And again, that's all I really did here. I took this thing, proved it was an indeterminate form. I don't know what this is, so I'm going to use L'Hopital's to prove that. I applied a logarithm. I brought the power down, or excuse me, I brought the power down, and then I turned that x in the denominator. Then I did L'Hopital's once I had this indeterminate form, and I get 1. And in this particular case, since I applied a logarithm, I have to exponentiate to get rid of the logarithm and actually get this particular limit.